So today I'm going to talk about whether we could actually make AGL functionally safe. This is something I had a conversation with Ambassador Ishii at the Embedded World in 2022 about basically making Linux safe. Not really possible, but let's see if it is. Okay, so I'm going to talk about building a better instrument cluster since the logo for AGL is an instrument cluster. How to make AGL safe. Talking about ASIL QM decomposition for safety, so spoiling a little bit there. And then a cockpit IVI for SDV, and then some conclusions. What did I just do? Yikes. I pushed the wrong button. Here we go. Okay, a little bit about Elektrobit. So I work for Elektrobit. We have an office about a half-hour walk here in Berlin. Our main office is in Erlangen, Nuremberg, across the street from the Fraunhofer Institute, where they developed MP3 back in the 90s. We've been around for 35 years, powering 5 billion devices worldwide, 600 million vehicles on the road. So basically, Elektrobit is a big name in automotive software. We're 100% subsidiary of the Continental Group, now going to be called Almovio soon enough. Okay, a little bit about me. I'm from the US, as you can tell from my accent. I got in the automotive industry in grad school in the 42-volt consortium, along with some of the big names like Daimler. Anybody remember that, the 42-volt board nets? I have a master's from MIT in Cambridge, Massachusetts, and a bachelor's in German studies from Swarthmore College near Philadelphia. I was with BMW for most of my career, from 1998 until 2011, mostly in Munich, but partially in the US. Then I was with Wipro. Then I was with Open Synergy for 7 years. So that's how I got deep with Panasonic, because Open Synergy belonged to Panasonic. That's also where I got deep into hypervisors. Open Synergy is located in Friedrichshain on the other side of Berlin. Most of Open Synergy now belongs to Qualcomm. I live in the Spreewald, which is about 100 kilometers southeast of here. Very beautiful place. If you're a nature lover and looking for something to do this weekend, talk to me in the break. I can give you some tips. I thought I would be the person that lived the closest to this site, but there are some people who actually live in Berlin, and I'm about 100 kilometers away. So, as far as my age, when I got married, Jerry's son was in grade school. Talking about age and marriage, my wife is actually from around this area, and she would have not been allowed to come to this neighborhood, which is very attractive, shopping on the Kudamm, the zoo, but she would not have been allowed to come here until she was a teenager. So, tells you about how old I am. Hobbies. I'm into amateur radio. Here's my call signs, German and US call sign. Also, since I live in the Spreewald, where there's many canals, when they freeze over, I do ice skating, and when they're not freeze over, I kayak on them. This is me putting up a tower for a ham radio antenna. I don't know if it's really safe, but today we're talking about software safety. Here's a picture of me doing free DV on my ham radio setup. And if Jerry is allowed to talk about his cat feeder, then I'm going to talk about my radio. So what you see here is me doing a mode called free digital voice on shortwave using my amateur radio. Here you can see my Japanese ICOM 746 ham radio. And what it illustrates is three things: the power of software-defined, the power of openness, and the power of artificial intelligence. So this mode, you can see, is running on my PC. I'm basically talking to people via my radio using my PC over shortwave. The real revolution for software-defined was the PC sound card, right? When PC sound cards came up, now you could connect the audio of your radio to the PC, and you could use any N or decoder that you wanted to use, right? So that was a huge advancement that came up in the year 2000s, right? Because my radio, when it was built in like 1990, the Japanese person who designed it was not thinking about digital voice. They were thinking of Morse code, which is great because I don't need a lot of power, so I can talk to Japan easily with Morse code, but slow data rate, steep learning curve, you need a lot of skill, and single sideband voice, which is not so great because you need a lot of power and the audio quality is really bad. It's like this, right? 3 kilohertz audio bandwidth, only good for old men, not women, not young people, right? So then some guys recently came up with what's called free digital voice, where I use my PC to N and decode it, and recently they came up with an NN decoder that used artificial intelligence. So instead of coming up with some rules-based thing like the old MPEG decoders, they basically said, okay, we're going to train a neural network. This is what things sound like coming over the shortwave channel. This is what it sounds like when it goes into the radio. And they train this model. And this basically allows me, using a computer with open source software and artificial intelligence, instead of needing hundreds of watts to talk to somebody in Japan with really horrible audio quality, now I can do it with probably 50 watts and have really, really good audio quality. So that shows, again, openness, software-defined, and artificial intelligence. What great things you can do. Okay, enough about ham radio for now. Let's build a better instrument cluster with AGL. So the instrument cluster telltales have the ASIL-B requirement, right? Which is generally why you couldn't use purely AGL to build an instrument cluster. You always had to do something else, right? The function is to notify the driver of important events or vehicle malfunctions. The safety requirement is that the driver must be informed if the system is incorrectly displaying the telltales, right? Here's the telltales. And if there's a problem, you got to flag a warning so that the driver knows, okay, I can't trust this thing. For example, I don't know, I don't usually check my tire pressure because I'm like, if my tire pressure is low, then the tire pressure monitor will signal to me on the cluster that, you know, my tire pressure is low, right? And I come to rely on that. And if I can't rely on that, then I need to know that I can't rely on it. That's the requirement. Nothing new here. Okay, so how have we seen safety will be realized on AGL? So basically, it requires using real-time software and hardware. So here we have real-time hardware and software. So here's our AGL, that's QM, right? Then we do our telltale checking over here on top of some AutoSAR OS, which is real-time, on top of real-time cores, the safety island, essentially. And sorry, over here you have your performance cores, your Cortex-A, 78AE, and all these things. Okay? Now we have performance cores that are safe, ARM-AE, for example, at least up to ASIL-B. So we can do safety on the performance cores. We don't need the safety island anymore for our telltales. But still, we need some kind of software that is there. Zephyr, right, is basically being proposed. So that's fine, but we have a pretty complicated architecture now where we're doing the checking here. We have AGL over here. And another problem is we're essentially using real-time software where we don't have real-time requirement, right? And safety is actually not equal to real-time. Everyone thinks, oh, safety, I need real-time. Because basically, if you wanted to do safety, the only software and hardware that supported safety in the past was real-time because it wasn't as complicated. But that's not the case anymore, right? Now, if you don't have hard real-time requirements, you don't need real-time hardware and software, right? So I'm defining real-time, throwing it out there because it gets defined in a million different ways. I'm saying it's the combination of determinism and low latency, right? So if I say, okay, only determinism, that could be, okay, if something happens every 10 minutes, would you call that real-time? Probably not, right? But if it needs to happen generally every millisecond, then you start getting into real-time, right? But that's not an instrument cluster, right? There's a person behind it. You know, if my instrument cluster fails, if I notify the driver, 500 milliseconds sooner or later, it's not really going to make a difference. So actually, we have a safety requirement, but we don't have a real-time requirement around the instrument cluster, right? And this real-time hardware and software, it's limiting our usable feature set. Like, Zephyr's cool, but it doesn't give me like a rich POSIX interface like Linux does, right? It's going to limit my compute throughput. These things are optimized for determinism. They don't have caches generally. They don't have, out-of-order execution. This makes them deterministic, but it makes them less powerful from a compute point of view. And of course, they add complexity to the development process. Now I need to have developers who know how to deal with Zephyr, who know how to deal with this real-time hardware. So using real-time stuff is great when you have real-time requirements, but when you don't need it. So it's better to use the same feature-rich, high-performance hardware and software for safety as you use for the QMWorks loads. So let's use AGL for the safe instrument cluster, right? Okay, so let's imagine the possibilities. Here's Elektrobit's instrument cluster. Could also be Panasonic's instrument cluster, no problem. And here you have the telltales being rendered by a gaming engine, in this case, Epic Games' Unreal Engine. Okay, there we have our telltales. But we also use artificial intelligence to theme the instrument cluster. So you can say, oh, you know, I'm in kind of a, you know, I'm not in a black mood today, I'm in a brown mood. And then the instrument cluster will change to that, right? Now your telltales are up here, right? So now your software that's monitoring these telltales or rendering these telltales is getting more complicated. It may be difficult to do that in a real-time context with real-time hardware because your telltales are moving all over the place. Up until now, your telltales had always been in the same place and they'd always been pretty primitive. Now, by using high-performance compute hardware and software, we can do a lot more interesting things with the telltales. Okay, but we still have the problem that we would like to do them on our high-performance compute operating system on top of AGL, and AGL isn't safe, so we have a problem. So how do we solve that? How to make AGL safe without actually making it safe? The plot thickens. Okay, so what exactly are we trying to prevent? I talked about it before. We have our safe application. That's the stormtroopers. We have our safety requirement, keep the droids, R2-D2 and C-3PO on Tatooine because they have the plans for the Death Star, right? And so everything's under control. We have our safe application, it works, everything's great. The problem is Obi-Wan Kenobi comes along and he mind controls the stormtroopers to not find the droids, and it's the beginning of the end for the Empire, right? So what's the big problem here? The big problem is not that the stormtroopers failed at their job. The big problem is Darth Vader didn't find out about it. It went undetected, right? And if you look at Linux, the Linux kernel, Obi-Wan Kenobi, has total control over all the applications, right? It can mind control my safe application, right? Without me detecting it, right? If the Linux kernel takes down my application, I'll have a software watchdog or something, and I'll detect that, right? If Luke and Obi-Wan bust out their lightsabers and cut down these stormies, yeah, then Darth Vader's coming down and he's going to get the droids, Empire saved, right? But that's not the problem. It's these subtle issues that we're trying to solve here that can be unforeseen, right? Like Darth Vader didn't foresee some Jedi coming along and mind controlling his stormtroopers. After Order 66, there aren't any Jedi left, right? So often these things are unforeseen, but we need to make sure that we find these subtle things and flag them. So that's actually what we're trying to detect. So again, we're not trying to, detect the easy things like my application crashing and there's no telltales. That'll be pretty easy to detect. What we're trying to detect and prevent is my application looking like it's working right, but it's not, right? I think my cluster's working. My tire pressure's down in the tank. I need to refill my tires, but my cluster's not telling me. Let's talk a little bit before we get into how we're going to make Linux safe about safety and open source. And that safety is not a quality level. So Linux, including AGL, is a high-quality piece of software, right? Works well. There is even automotive spice processes on top of it. It works well, so that's awesome. The problem is there's no safety requirements. There's no safe development process, although we did learn yesterday that you could potentially make Linux MISRA conform with a lot of argumentation, so you could maybe get a piece of the development process, but up until now, not. And of course, there's no safety documentation. And as somebody said yesterday, the motivation of the Linux community to make Linux automotive safe is low because most Linux deployments are not in automotive. So why are you going to expect all these people in their free time to work towards automotive safety standards when they don't care, right? So it's not going to happen. But that doesn't mean that just because Linux isn't safe doesn't mean that it's not good. It is good. I think we're all convinced of that. So what qualification approaches can we take? Someone else talked about this yesterday too. We can do a full project qualification where the whole open source project is all in on safety. We just learned about Zen. Kazakabe-san just talked about Zen. That's it, right? We've got a strong corporate sponsor, AMD, right? The whole project is behind it. They're going to do automotive safety in Zen. Awesome, but also pretty rare, right? There aren't that many AMDs in this world who are willing to finance something like this, and there aren't many open source projects that are willing to go that way. Linux, probably not. Then you can do a snapshot qualification where you essentially take a snapshot of what there's now. It's something good like Linux, you fork it, and then you argument that it's safe. Like similar to Roberto's argumentation yesterday of Misra, you do that with the rest of the stuff and you can say, yes, it's safe. So example projects of that are Karen Concept's L4RE, EB Corbos hypervisor, microkernel, which is basically forked. And of course, this is what Red Hat is doing with Linux, right? They're essentially forking it and saying, yeah, we're going to put safety processes on there and say that it's safe. Or you can do ASIL QM decomposition, and that's what we do. You essentially take the project as it is, it develops as it is, and you put some monitoring on there on top to ensure that that thing is safe. And that's Elektrobit Corbos Linux for safety applications. And now I'm going to talk about how we do that a little bit. First, let me compare the qualification approaches from technical implications. The big takeaway is if you do full project qualification, it's a lot of effort. When you look at Xen, it's a lot of effort. But AMD's financing it. The community needs to be on board, and it's not really in line with current safety practice in the automotive industry. If you do a snapshot qualification like Red Hat's in-vehicle operating system, it's difficult to maintain because now you've got a fork. Forking is like not a good setup, right? It's also a lot of effort, right? Red Hat's been working on this for years and years. You need the community and the qualifier to be on board, so you need to exert some sort of control over the open source community, which also may not be easy. If you're Red Hat and it's Linux, maybe, and it's not really aligned with current automotive safety practice. ASIL QM decomposition. It'll only work in some cases. That is the big problem. It won't work for every project. You need to find a project where it works. We're convinced that it does work for Linux. But it's easy to do from a maintenance perspective because I don't really care about what I'm trying to make safe because I'm monitoring it from the outside. So I don't have to fork, which is a huge advantage, right? The effort initially is low. I just need to make the safety monitor. The process adherence is by the qualifier. So Elektrobit has done this for Linux, and we're the only ones that have to adhere to process. The Linux community doesn't have to do anything. And it's aligned with current safety practice. It's essentially doing the things that automotive safety people know and love to do. As opposed to, for example, Roberto yesterday was saying, well, for Misra, we could do this, that, and the other. The argumentation, yes, certainly would work, but it's not really the way that things have been being done in the past. Okay, from a commercial point of view, big takeaway is the invest for full project and snapshot is high. It's a lot of work, as we said. For ASIL QM, it's low. Maintenance, okay, for example, for Xen will be good because the upstream project is going to do it. For snapshot qualification, it's very difficult because you make something safe, and you have to maintain the Linux kernel. Otherwise, it's a cybersecurity mess, right? So you can say, okay, I'll just snapshot it and freeze it, right? But then you've got safety, but you've lost cybersecurity, right? So ISO 26262, check mark. ISO 21434, dead, right? Whereas, of course, if you do a decomposition, then there is no maintenance cost because you just let the open source project advance as it has been. Monetization is not so great when you do full project qualification. I think AMD is not financing Xen ASIL D qualification to make money, but because they want to use it and they want to make money from that. They're probably not going to make money off Xen. With a snapshot qualification, you can monetize the IP and the safety-related artifacts. And with ASIL QM composition, you can also monetize the intellectual property and the safety-related artifacts, such as the safety monitor, for example. Okay, so how does this all technically work? Or how could it work for AGL? So what we did is we created separation layers, right? Here's we have our safe application. This is actually what we care about. So for years, the industry has been saying, we need a safe Linux. We need a safe Linux. And we actually, 6 or 7 years ago, tried to make a safe Linux for a German OEM and totally failed. Linux kernel, too big, and it's a maintenance nightmare. So we took a step back and said, you know what? Actually, you don't need a safe Linux. You want safe applications running on Linux. And that's what we did, right? So here's our safe application. They still have to be safe, right? We don't have some magic that makes an unsafe application safe. And that's not easy, making these applications safe. You need safe libraries, safe compilers, all these things you still have to do. But what we did is we assumed the Linux kernel now is unsafe. The Linux kernel is kind of a bad boy, right? Fast innovation cycles, very feature rich, but a bad boy. And we use the hypervisor to essentially, or a monitor in hypervisor mode, to create freedom from interference between the Linux kernel and the application. So our potentially naughty Linux kernel cannot mind control our safe app. Like Obi-Wan Kenobi cannot mind control the stormtroopers anymore. That's basically what we did. And this OS safety monitor lives within the hypervisor. We're currently using the L4RE microkernel from Karen Concept in Dresden, but looking to move to, or support Zen in parallel to that. And we have this OS safety monitor, which is essentially sitting on the memory mappings of the Linux kernel and taking write access away from the Linux kernel for the safe application, right? So now the Linux kernel cannot write into the safe application. So what we get, the safety hinges on the OS safety monitor, the hypervisor, and of course the SoC. We still need to have safe hardware underneath, as I talked about. We need those Cortex-A, AE cores to be safe. The Linux kernel has no safety allocation, so you can update it all you want. You maintain the speed, which is one of the great things about the open source community. You're not slamming on the brakes of the open source community, yeah? Integrator can add custom device drivers, and it can be replaced by another distribution. So we offer this now based on Ubuntu, but it would be easy to make this solution work with AGL, which is why I'm standing here today, right? So that's awesome. Now, someone may say, well, look, if the Linux kernel can't write into an application, that's awesome. But how does an application get data, right? If I do like a network read, then the Linux kernel needs to write that data back into the application. So our OS safety monitor not only monitors the memory, it also monitors any syscalls, right? Otherwise, we would have an application that is safe but is useless because it can't do any I/O. Right? So that would be like a car. If you want to make it safe, take the engine out. It's safe. OK, so what achieved guarantees do we have? We have spatial freedom from interference. This is the memory protection, right? Obi-Wan Kenobi can't mind control the stormtroopers. We have temporal freedom from interference. The kernel cannot block applications indefinitely. We just talked a little bit about, Kazuka-san just talked about the Linux scheduler. It's very complicated. You will have some time requirements. We don't bother with it. We have a software watchdog that basically lives in the OS safety monitor so that the Linux kernel can't spoof it. And if it doesn't get a heartbeat from a safe application in a certain interval, it's going to raise the red flag. So again, we're monitoring the situation. We're not trying to make the Linux scheduler somehow safe. We do provide communication integrity, so shared memory communication is protected. This is done by the microkernel, the L4RE microkernel, and we also have startup integrity, which is very important. We make sure we have what's called a safe bootstrapper, which makes sure that whatever software you planned to execute also executes. We'll have to work in tandem generally with the secure boot solution of the SoC. Usually trust zone is involved. OK, so putting it all together, what is the difference between our QM ASIL decomposition approach and, let's say, Red Hat's snapshot approach or Xen's approach? So we have decoupled quality from safety. So here we have a trapeze artist at a circus, right? Then we have the audience here, right? If he falls down, that's a safety issue, right? He's definitely going to get injured, and people in the audience may also get injured. So what Red Hat and others have done is they've said, fine, we're going to make this trapeze artist so good that he won't fall down, right? We're going to train him and test him and test him and test him, and he's so good he won't fall down. So it's essentially a quality argumentation for safety. It's difficult because you really got to train and test this guy, so it's a lot of work. It's also difficult because he's a trapeze artist. So like the Linux kernel, he's pretty fast and loose, right? He's pretty talented, he's a genius, but he's also, a little fast and loose. So you never know what this guy is going to be doing at night, right? So maybe he's safe today, maybe he's not safe tomorrow. So that's a little tricky. What we do is we say, okay, this trapeze artist, he can do his thing. We care about quality, because if this trapeze artist is falling down all the time, then this is a cruddy circus, right? People aren't going to pay for it, and I'm going to go out of business, right? So I can't ignore quality, right? My trapeze artist has to be good, but if he does fall down, I put up this safety net, right? And so now, nothing can happen. So now I don't have to worry from a safety perspective about the trapeze artist and try and make him safe. All I got to do is worry about making this safety net safe, which is a lot easier. I may need to make sure that it's produced to the right quality. I may need to make sure that the anchoring in the wall is up to code, right? But that's a lot easier than trying to make this wild and crazy, fast and loose trapeze artist safe. So essentially what we did looking at the architecture to recapitulate is essentially we made the microkernel safe, similar to what the Zen community is doing, making the Zen hypervisor safe, and the OS safety monitor safe. And the OS safety monitor is really just a very small application. So what we're making safe, and this is the typical safety decomposition argument, what we're making safe is really very small pieces of software that are very simple, as opposed to the Linux kernel, which is very big, very complicated, and also very dynamic, changing very often. Okay, finally we get to the architecture. So this is what it could look like. Here we have a communications hypervisor. Here we're still doing our ASIL D stuff, because we can't get to ASIL D yet on the performance cores, and anything that's real time we're still doing over here, right? We still have hard real time requirements, so we still need this stuff over here. We have a hypervisor, we have a QM partition doing something, and here would be our cluster, right? We have a QM partition potentially doing the rendering using AGL, and then doing generating the telltales using the gaming engine, and here we are actually rendering or checking the telltales. So we could render them using QT's safe rendering, for example, here, or we could check them and then render them to non-safe hardware. So here's where we're doing that, and of course we could even simplify things and put these two together. That would also work. So we'd have one AGL partition running our whole telltale application, including safety, and we can do a lot more rich things, and we can reduce complexity. So that's basically it. Am I over time? I hope not.
You have 1 more minute.
1 more minute. All right. So anyway, functional safety is a baseline requirement for automotive software, especially in regulated markets. Like generally, the telltale ASIL B requirement is not going away, right? Now you have high performance compute platforms which enable safety. Also, so you can build now rich instrument clusters. Also, of course, ADAS is a big one, which is coming up, and autonomous driving. Automotive-grade Linux is not functionally safe by default, but with the right architectural approach, it can be used in safety-critical systems. So our approach will work with any Linux system. Now we could easily take this roadblock away and make AGL safe. Using an ASIL QM decomposition strategy, which simplifies qualification and maintenance greatly, worrying about the safety net and not the trapeze artist. And it also makes it possible to leverage the benefits of open source, such as flexibility and cost efficiency, right? So, we are all fighting the battle, maybe concluding words, fighting the battle of trying to convince OEMs to use Linux and open source in there, and being able to say, hey, it's safe, is definitely going to help us make that argument. That's it. Thank you.
So we have time for a question. Anybody have a question?
Could you go back to the slides of the architectural? Yes, exactly that one. I want to comment or question. I see, because we want to support different OS on the different cores, like RTOS and the Linux. I see stuff moved away from Linux into firmware, like pin muxing and all that kind of stuff, which Linux cannot handle on its own anymore because another RTOS. So is there can your safety monitor, is it prepared for also observing the firmware doing the correct stuff?
So that would be, observing anything is really the job in our setup of the safe application. All our monitor does is make sure that the application is going to execute the way that it should, the way that it's designed. So you really would have to have an application if you wanted to monitor a PMIC or something like that. One problem that we do have with our approach is that we are taking the Linux kernel out of the safety scope. So if your drivers are in the Linux kernel, then they would not be safe, right? So you'd have to move your drivers to user space or put them directly on top of the hypervisor. Does that make sense?
Yeah, I need to think about it. If you can have an application monitor the PMIC, because it does not know what the RTOS wants to do. It can maybe check what Linux wants to do, but not what the RTOS wants to do. So this is, I need to think. My gut feeling is it can't be done this way, but I have to think about it.
Okay. I'll be around all day, so.
All right, so it's time for a break. If you want to stick around and ask a few more questions, I'm sure Isaac will answer them. Otherwise, there's coffee and treats outside. And I got to go find our next speaker, too. So thanks, Isaac. And if everybody wants to stick around, you can ask him some more questions.
Or I may go out there, too.